Hoover Dam is one of the most staggering things human beings have ever built. 726 feet of concrete wedged into a desert canyon, taller than a 60-story tower, holding back the largest reservoir in the United States. They finished it in the depths of the Great Depression, 2 years ahead of schedule, with tools you'd now find in a museum. 90 years later, it still stands, still holds back that reservoir, and still turns the Colorado River into water and power for millions across the American Southwest. Stand at the base and look straight up, and it feels less like a structure than a mountain someone decided to pour. The concrete is fine, it will stand for 1,000 years. That was never the problem. Because deep inside that mountain of concrete, below the waterline, there's a machine, 17 turbines that have run almost without pause since 1936. Powering 1.3 million people across 3 states. And right now, that machine is quietly beginning to tear itself apart. Not the dam is immortal. What's failing is the thing that makes it useful. To understand why this matters, you need to understand what they built and how they built it, because the scale of what was accomplished in the 1930s is the only context that makes the current failure feel as strange as it actually is. The Colorado River had to be moved before a single yard of concrete could be poured. Frank Crow, the superintendent who would become one of the most celebrated dam builders in American history, solved this by blasting 4 diversion tunnels through the canyon walls, 2 on each side of the river, each of them 3/4 of a mile long and 56 feet across. To drill them fast enough to meet the government's punishing deadline, he invented what became known as the jumbo rig, a steel frame carrying 3 tiers of drillers stacked on a 10-ton truck that let 30 men work a rock face simultaneously instead of one. The tunnels were finished ahead of schedule. Then came the concrete, more than 3.25 million cubic yards of it, poured in interlocking blocks 50 feet square and 5 feet deep. The problem was heat. Concrete generates enormous thermal energy as it sets, and if Hoover Dam had been poured as a single mass, the heat alone would have taken an estimated 100 years to dissipate, cracking the structure from the inside long before it was ever finished. Crow's solution was more than 582 miles of 1-inch steel pipe threaded through the blocks, carrying refrigerated water from an on-site ammonia cooling plant capable of producing 1,000 tons of ice per day, the largest refrigeration system built at that time, running continuously for years, pulling the heat out of the concrete block by block. When each pipe finished its job, it was filled with grout and became part of the dam itself. By 1935, the dam was structurally complete, and by the end of 1936, the powerhouse was generating electricity, built during the Great Depression with 1930s tools by a workforce that had never done anything like this before. And from that day to this one, the river has never stopped it. If you've played Fallout New Vegas, you already know this building. The whole game turns on who controls Hoover Dam, because whoever holds the dam holds the power. That's not just a game writer's fantasy, it's the actual reason this place has always mattered. Before any of that concrete could be poured, the canyon walls had to be cleaned. Every loose rock slab and unstable outcropping stripped away, so the dam could anchor to solid bedrock. The men who did that work were called high scalers, and their job was exactly what it sounds like, descending the canyon walls on ropes with jackhammers and dynamite in temperatures that regularly exceeded 120 degrees at the canyon floor. Falling rocks and dropped tools were among the most common causes of death on the project. The men began coating their cloth hats with coal tar to protect their skulls, what they called hard-boiled hats. Even men hit hard enough to break their jaws walked away without skull fractures. 6 companies contracted for commercially made versions and issued them to workers on the site. What the high scalers improvised in Black Canyon helped give rise to the modern hard hat. The official industrial death toll for the construction is 96. Men killed by falling rocks, heavy equipment, canyon falls, and drowning. That figure comes from the Bureau of Reclamation, and it does not include the workers who died of heat and pneumonia in the same years, nor the very first casualties, who came years before construction even began. And it's those first and last deaths that are the strangest thing about this place. On December 20th, 1922, 6 years before the dam was even authorized, a Bureau of Reclamation surveyor named J.G. Tierney drowned in the Colorado River while scouting the site. He was the first death connected to the project. 13 years later, to the exact day, December 20th, 1935, his son, Patrick Tierney, fell from one of the Arizona intake towers. He was the last man to die during construction. The Bureau's own record puts a father at the beginning and his son at the end, 13 years apart, on the same December day. If your family worked on the dam, tell us in the comments below. The story everyone is reporting about Hoover Dam is about the water, the bathtub ring on the canyon walls, the retreating shoreline, the shrinking reservoir. That story is real, but it's not the most urgent problem at the dam right now. The most urgent problem is mechanical, and it's happening inside the powerhouse. Hoover's turbines are a Francis-type design. They convert the pressure of falling water into rotational force. The amount of pressure available depends on what engineers call hydraulic head, the vertical distance between the water surface above and the machinery below. As Lake Mead drops, that distance shrinks, and so does the pressure. Below a certain point, something called cavitation begins. Cavitation is what happens when water pressure drops low enough that bubbles of vapor form inside the flow and then collapse violently against the blades. Each collapse releases a tiny shock wave. Individually, nothing, but across millions of cycles an hour, they physically erode the steel, pitting and gouging and eventually destroying the blade surfaces from the inside, while the machine still appears to run normally from the outside. Recent technical assessments by the Bureau of Reclamation found that the older turbines are likely to suffer severe cavitation damage below Lake Mead elevation 1,035 feet. At full reservoir, Hoover generates 2,080 megawatts. Years of drought have already cut that to 1,304 megawatts. And if the lake falls below 1,035 feet, and 12 of the 17 older machines have to be shut down to keep from destroying themselves, that capacity collapses to 382 megawatts, from 1,304 down to 382 at a single line on a gauge, a 70% cliff. Generation is already down roughly 30% from the dam's rated capacity. The concrete is not the threat. The concrete will outlast every person watching this. The machines are the threat. As of late July 2026, Lake Mead sits at elevation 1,041.1 feet, about 6 feet above the line where severe cavitation begins, and just half a foot above the lowest level ever recorded in the reservoir's history, the 1,040.6 feet it hit in July 2022. The Bureau projects it will keep falling. Tom Bushatsky, director of the Arizona Department of Water Resources, said it at a public meeting without softening it. We're going to go to 1,035. No question, it's going to happen. On May 21st, 2026, the Bureau of Reclamation released $52 million from the Hoover Dam Post-Retirement Benefit Fund for critical maintenance and for the replacement of up to 3 of the older machines with a new design called a wide head turbine, a redesigned blade geometry that lets the powerhouse keep operating at lake elevations approaching 950 feet without suffering the same cavitation damage. It extends the dam's operational range by 85 feet of lake elevation below the current danger line, and each one restores at least 160 megawatts. The gap that decides whether this works isn't an engineering problem, it's a timing problem. 2 of those replacements may not be finished until October 2028. The lake was about 6 feet above the 1,035 line, and within a foot of its all-time low when this video went up, and falling. The question the Bureau cannot answer with certainty is whether the water crosses that line before the new parts arrive, and what the damage to the old machines looks like if it does. Jordi Fuentes, executive director at the Arizona Power Authority, was blunt about what that means for the people who buy this power. We're basically knocking out most of Hoover's generating capacity. When that happens, the resource becomes unaffordable for most of our customers. A large part of the audience arriving at this video carries the same objection. No amount of engineering fixes a reservoir that's running out of water. That objection is not wrong, but it misreads what the $52 million is actually buying. The redesign does not solve the drought. It extends the operating window, pushing the damage threshold from 1,035 feet down toward 950, and buys the system time to either recover or adapt. Whether that's the smartest engineering bet of the decade or the most expensive way to lose slowly depends entirely on what the lake does next. Both answers are still live. The machines are the part they can afford to fix right now. The full picture is larger. The Bureau of Reclamation estimates roughly $200 million in maintenance needs at the facility over the next decade, and the Army Corps of Engineers classifies Hoover as high hazard. That designation is about the consequences of failure for the communities downstream, not the dam's structural integrity, which remains sound. And below the minimum power pool, the picture changes in ways that reach far past the price of electricity. Water that currently flows through the turbines would have to be routed through the outlet works, lower capacity pipes never designed to handle sustained high-volume flow. At that point, the dam's physical limits, not the turbines, begin to govern water delivery across 7 states. The consequences spread from electricity to irrigation to the drinking water of a region of 40 million people. Underneath all of it sits one number from 1922. The Colorado River Compact allocated more water than the river actually carries in an average year, because the measurements were taken during an unusually wet stretch. That overallocation sits beneath every other problem at Lake Mead, and it has no engineering solution. Go back to the powerhouse. 17 turbines, 9 decades of continuous operation. The machine that Depression-era workers built in Black Canyon 2 years ahead of schedule, with tools that would look primitive today, that machine is still running. It powered the Southwest through the 20th century and into the 21st, and it's still producing electricity right now, while crews prepare to open it up and replace its blades before the lake takes the decision out of their hands. The engineering was a masterpiece. The surgery is underway. Whether the surgery finishes before the patient crosses the threshold is a question Lake Mead's elevation will answer, and nobody controls that timeline except the river. Minimum power pool is elevation 950 feet. Lake Mead is at 1,041 today, just half a foot above the lowest it has ever been. The distance between the water and the point where this machine goes quiet is the narrowest it has ever been in the dam's history, and it is still closing. So here's the question this leaves you with. The people who built Hoover Dam finished 2 years early with 1930s tools. The people who maintain it today can't guarantee the parts arrive before the water drops below the line. What changed, the engineering or the will? Drop your answer in the comments. Subscribe for more Megabuild stories like this one. Thanks for watching.